Hi everyone and welcome to this reinforcement learning presentation. This is going to be an introductory talk. We will cover the most fundamental concepts of reinforcement learning. My name is Sven and in the following 45 to 50 minutes we will look at the problem type that reinforcement learning is able to solve, and thereby we will learn that all reinforcement learnable problems share a common formalism. It's called a Markov Decision Process, or short MDP. We're going to look at in all detail at what this is. We're going to define it and run through an example, and we're also going to build our own MDP, which will be a simple game, and then we will run a reinforcement learning algo over this game. And we will try to find out whether this algorithm can actually solve the game. The algorithm we're going to use is called Q-learning, and while we're doing this step-by-step walkthrough, we will gain an insight into how the algorithm works, how it handles exploration, how it handles decision making, and so on and so forth. And lastly, we're going to look at state-of-the-art reinforcement learning. I'm going to briefly introduce a couple of recently published research papers, and we'll talk a little bit about the mathematical models being used nowadays, which goes into the neural network deep learning area, and hopefully we'll get an understanding of the complexity of problems that we are already able to solve with reinforcement learning. And I will also try to make a bridge between this algorithm that we use here to solve our game, which is a rather simple algorithm, down to the more modern state-of-the-art algorithms. And it's going to be interesting to see which concepts have changed and which concepts also have stayed the same. So let's start. What is reinforcement learning? Reinforcement learning is the art of solving a Markov decision process, or short MDP. And in the next couple of steps I will explain in all detail what a Markov decision process is. An MDP can look as follows. We have an environment, this thing here, and the environment changes over time. So there's a time component to this whole thing, which is why it's called a process. And just imagine like some global clock object that ticks along as the environment changes. And at each time step, the following things happen. We will make an observation of the current state, and this observation we call S stands for state. We will then make a decision on what to do next. And in this particular case, we have this agent here that lives in the environment. It's agent Pac-Man, and this agent can move either up, down, left, or right. And these are our 4 actions that we can pick from at each time step. So in this time step, we decide to go up, and then we're going to execute this action. And now 3 things will happen. First of all, the clock performs a single tick. The environment changes. We can see that Pac-Man moved up, which is always called, denoted with a prime meaning the next one, so we make a next state observation. And the reason for the change of the environment is not always only the action that we took, but there could also be other elements, like these ghosts here, that add some dynamics to the environment. So it may change either way, whether we act or not, or independent of our actions. And the third thing that happens is we receive a reward signal. And this reward signal is a single scalar value. It can be negative or 0 or positive. And of course, you can imagine that this will enable us, or this enables the designer of the MDP to insert domain knowledge into the system, and hence to be able to communicate with our algorithm. So that the algorithm has it easier to solve this problem. And this whole thing here constitutes already a single step, a complete loop in the Markov decision process. And what's happening now is that we just repeat this a billion times. So based on the next state, on S prime, we're going to make a next action decision, A prime. This time we're going to go right. We're going to execute this action, and again, three things will happen. The time will move on. We're going to yet observe another state, S prime prime. You can see that Pac-Man is moving here. And we're going to receive a new reward signal, which this time is +10 because we ate this this cookie here, this one here, and this is also reflected in our game score. Now you can also interpret this whole process, and again, this is just 2 steps, but in reality we're going to do many steps. This could go into the thousands or 10,000s of steps before this is over. You can also interpret this whole sequence of events here as an API, where the MDP is a class and the class has a step method, and in some kind of for loop, right? You call this step method over and over again, each time giving it an action that you would like to execute, and as a return value you will receive a reward and a next state observation. So every problem that you can possibly think of that that fits this API, that you can squeeze into this formalism, is a Markov decision process and can hence be solved using reinforcement learning. And now at the very end I also want to talk about what solving actually means. It's quite simple. Solving means we find the optimal policy, and a policy is the selection of actions throughout time, and it is a function always called pi in the literature. Pi star means it's the optimal one, and it's a function that returns an action if I hand it a state. Yeah, so it basically tells me what to do in each state. It takes this role of the decision maker here, and solving means to find the optimal policy, which is the one that maximizes the sum of future rewards. So if I add up all these R values over time, I want to maximize those, and the optimal policy will always choose actions, will always return actions based on the current state that maximize this sum. Yeah, that's what solving means. Okay, so I want to talk a little bit more about the reward function really briefly. This is just something that I want to do before we move on and build our own MDP. The reward function can be interpreted, as I already said, it's a way for us to communicate with the algorithm, and it can be interpreted as a as a settable parameter that specifies how supervised my MDP is, or my problem is that I want to solve. So we have unsupervised learning methods, and we have supervised learning methods in the machine learning universe, and reinforcement learning is considered to be somewhere in the middle. And the reason for that is, if I imagine a reward function that is very sparse and delayed. Sparse means it's almost always 0, and delayed means that after I take a very good action, a very smart action, the reward for that may show up 100 time steps or 1,000 time steps later. Okay, so if I have a reward function that looks like that, it is incredibly hard to solve this MDP, and it goes more. The problem becomes more of an unsupervised problem. On the other extreme, if I slide this slider all the way to the supervised learning methods, in that case my reward function will look different. It will be very diverse. It will have a lot of values that are different from 0 and change a lot, and also these reward values will always come in very closely to the action, immediately closely to the action that are evaluated by this reward. Yeah, so I have no delays, and it's not sparse anymore. And then the whole thing becomes a supervised learning problem, kind of similar to neural network inputs paired with labels. So the labels would be the rewards, and the inputs would be my state action pairs. All right. Uh, I want to go back now to Markov decision processes, and as promised, we will build our own Markov decision process, which is a simple game. It's called the Crocodile Lake domain, and it looks like this. Well, let's simplify. So we have an environment. We have an agent here, this guy, and this agent is able to walk around the environment. So we have 5 states, which is, again, this is a really simple MDP. The states are denoted A, B, C, D, and lake. And D is the go state, meaning that we want to reach D. And the state of the environment is always the position of this guy here. So if this guy is up here, we're in state B. If this guy is right now here where he is right now, we're in state A, and so on and so forth. So the state space is discrete and it's finite. It's very simple. Similarly, we have to define the action space, always denoted with a capital A in the literature. By the way, the notation that I'm using here in this presentation is exactly the same as in the reinforcement learning literature. I use the exact same symbols mathematically as well as conventionally. Action space. So we have 3 distinct actions: north, west, and swim. Swim are these diagonal arrows. So, for example, if I'm in state A, I can swim and then I'll be in the lake. And if I'm in the lake, I can swim and then I'll be in state D. And lastly, we're going to define our reward function. We also make that very simple. We get -2 if we end up in state B or C, or we get +5 if we reach the go state. And once we reach the go state, the environment gets reset and the agent moves back to state A. Also, when we enter the lake, we will have a stochastic reward signal, which most of the time is going to be 0, but 10% of the time we receive a reward of -10 because the crocodile bites us. So before we run this algorithm over this problem, over this simple, really simple example problem, let's take a look at it manually with our own eyes. Let's take a few seconds and let's try to figure out what the solution is, what is the optimal policy in this environment. So we have, what options do we have? We could either go up here over to state B and then to D, which is the same as taking the path through C, because the reward here is the same. And so in both cases we would get +3, right? -2 + 5 is 3. And if we choose the lake path, if we choose to swim, we would get on average, when we enter the lake, -1, right? Because only every 10 times we get -10, which is better than this -2 here. So it's the solution to this game is that it's always better to cross through the lake and go diagonally and swim. So now what we're going to do next is we're going to introduce the Q-learning algorithm, which was invented or discovered by Watkins et al. in 1989. And we will see whether this algorithm is able to solve this MDP. Q-learning is a model-free reinforcement learning algorithm, and what that means is that the algorithm does not require any prior knowledge of the MDP model. So it doesn't need to know what the state space is. It will still get the observations of the current state, but it doesn't need to know what the state space is, what the other states are. And it does also not need to know the reward function. It will only, once it starts acting, receive the single reward signals, lowercase r. Then the next thing that I want to talk about is this is called a tabular algorithm. So we need a table. This is our table here, and the table represents our Q function. Now I need to explain what a Q function is. A Q function is something that's not limited to Q-learning. It's a very broad and fundamental concept in reinforcement learning, so it's important that we understand now what it is. Of course, Q-learning, the algorithm, was named after this Q function, but again, the Q function is generic, and it shows up in many other reinforcement learning algorithms. It's basically something fundamental to MDPs. Yeah? Doesn't really have to do anything with the algorithm. It's more fundamental to the actual process, the actual underlying process. So what does a Q function do? A Q function takes the current state that we're in and the action that we are intending to pick next, and it returns the expected accumulated future reward until the end of the episode. So for example, the Q value for the state A and action north, which is this guy being here and going north, is 3. Why? Because we're right now we're here, we would pick north, we get -2, and from here we only have one choice, we go west, and we get +5, and we sum this up, and that's 3. So now my next question is, what if we add more actions here to this B state? What happens then to this Q value? So again, the question is, what is the value of the Q function if I plug in the values, the state A and action north? Well, let's think. So the agent will go north, it will receive -2, but now what does it do? We don't really know, right? So it could go down to the lake, or it could go back to A and then to the lake, or it could go back to A and then to C and then to D, or it could go directly to D. But we don't know unless we know what the policy is, right? The only action that we have locked in is this north action. It's this very first action that we're going to take from this state. But we don't know what happens afterwards unless we know the policy. So the Q value, and that's why we write this pi here, because the Q value is always dependent on the policy. Yeah, and so let's define the policy. Let's say which policy this algorithm is using in order to move around and learn, so that we get this out of the way. The policy for this algorithm, again we call this pi, and it's a function of the state that we're in, is to always choose the best of all available actions for the current state, according to the current version of our Q function, of our Q table. Okay, so it's very simple. Well, if we're in a state, we look up all the values for this state, all the Q values for this state, and pick the one, and pick this action that has the highest value here. Okay? Alright. And once we start acting now in this environment, every step that we take, every action that we take, we will make one update to our Q function, and this will eventually populate our Q table. Yeah, so the default value is always 0 for every state action pair that we can think of, but we're going to make these updates, and this rule will help us to populate these values here once we start acting in the environment, and we will act following this policy. Okay, let's look at the update rule real quick before we start moving around. The update rule says that we're going to only update the current state and the action that we picked, the Q value for this pair. It's gonna stay the same value plus some small change. Yeah, alpha is called the learning rate, and 0.1 is a good value to start with. So we're gonna leave the value as it is, right? Except for some small change that we make. And now what does this change look like? This change is the difference between the new belief of this value, and the old belief of this value. This is the old belief, the one that we thought was the Q value before we made this step. And after we made this step, and after we've seen the reward for this step, we have a better estimate for this value here, because this is the same. This R plus max A prime Q S prime R prime is the same, or is corresponding or corresponds to this one here. It's just a better estimate of this one. So I take the difference of that, multiply with alpha, and that's my small change that I make to this very Q value. So let's start acting. We're going to pick a first action, And why did we pick action north? Well, because the policy says always choose the best of all available actions. Right now everything is 0, so nothing really is the best, neither north nor swim nor west. So we pick one randomly. And our random pick in this case was to go to the north. So we fill in all the values that we have. And let's do it on this side of the equation. So right now A and north is 0 because everything's 0. Our learning rate is 0.1, our reward is -2 that we have observed here. And our best next action, which is the action that we take from B, there's only one, and that's also 0 right now because we have nothing in the Q table yet. It's also 0, and this again was also 0, so the new value is -0.2, and we're going to put this here now. So our first action was north, and we can update the value for the tuple A north to be -0.2. Our next step is then to go west because there's only one action left. We're going to do the same thing again here. We're going to plug in the values. They are still all 0. And the decisive thing is again this reward signal that we're going to get. And because we have a learning rate of 0.1, our change is 0.5 for this B west value. Okay. So our current estimate for being in state B and taking action west is 0.05, which is not true. At the end it should be +5, right? But only at when we're done with learning. We're still learning right now. We're making small changes towards the final learned Q table. Now that we've reached the go state, we're going to reset, as we have said before, so that the agent goes back to state A. And now we're going to pick another action. And again, we have to look at the current Q values being in state A. So we could go north, which is -0.2. It's not so great. We could swim, which is 0, or we could go west, which is also 0, because we have never tried these and they're still using the default values. So this policy will choose either one of the swimming or going west, and in this case it picked swimming. And again, we do the update. We plug in everything, all the values that we have. The current value for A swimming is 0 because we don't have one yet. Alpha is always 0.1. The rewards that we receive, right now we received a 0. Thank God the crocodile didn't eat us. And the next action, this max A prime Q, is going to be 0 as well. Because from the lake, there's only one action, but there's only one A prime, which is swim again. We don't have a value for it yet. So we're going to get an update of 0. So A swim, right now our estimate for this is 0. Then we're going to do another step, the only possible one. Again, we're going to swim from the lake. So our state is lake, our action is to swim. And if we plug in all the values, we get 0.5, and we write this to our table. And now we get reset again, and now we're going to do this a lot of times. Alright, we're going to do a lot of single steps walking through the environment, and each step we're going to use this update rule to act, and then to update our table, to add values to our table, or to change values that are already in the table. Okay, and at some point when we're done, the table should look like this. Yeah, it should converge to the actual values that we have already figured out before, but just by manually looking at the problem. So it's true that A north has a value of 3, because if I'm in state A and I go north, I get -2 + 5, and so on and so forth. And now we can also see that swimming is the best action if I'm in state A. Yeah, and again, this is how this policy works. The policy says, okay, I'm in state A right now. So I'm going to look at the 3 different actions, which is north, swim, and west, and I'm going to pick the best one, which is the 4 here, right? The others are 3, so they're not so great, so I'm always going to swim. Okay, and thus this thing is solved. Okay, now we're going to skip about 25 years into the future, which brings us to from 1989 to the years 2013 to 2015. And in that time period, the Google DeepMind group in London, they published a couple of papers, I think it was 3, on on a new method that they have developed, which they call deep Q network. All right, and we're going to so these are still the components here. Let me switch on the pointer again. These are still the components here of the classic Q learning algorithm. And what we're going to do now is we're going to replace piece by piece here, element by element, of the old Q learning algorithm with what these guys have changed, so that we can watch the evolution from this method, from the original Q learning method, to a state-of-the-art reinforcement learning algorithm today, and watch this evolution, how it takes place. So the first thing that we're going to change, or that these guys changed, is the complexity of the MDP. It went up by a lot, as you can see. So they use this Atari 2600 games as their environment. And now the question is, what is the state space? So let's look at the state space changes. We're going from 5 concrete discrete states to a state space that looks like this. Now we're doing what I had indicated before when I introduced the MDPs. We're taking the actual pixels of these images while Pac-Man runs through the level, while the ghosts run through the level. Each frame of the game, we generate an image, and we encode this image as a 3-dimensional tensor. A tensor is a 3D matrix, or a matrix that's larger than that has more than 2 dimensions, and we're going to provide these tensors here as a state signal for our algorithm. Yeah, so the state space just exploded. All right. I didn't do the calculations, but I could imagine that it's more than 1 billion possible states that we can reach with this, given all these dots and all the possible combination of positions of dots and so on and so forth. So we can already see that the table will no longer cut it, right? So we would have, if we use the table, we would have to have one entry for each possible state that we encounter. So it's absolutely impossible. The next thing we're going to do is we are looking at the action space, how that changed, and it changed only marginally. The new action space is up, down, left, right, plus all the diagonals. Plus I think there was a button on the joystick which also goes in here, but it's still a relatively small number of available actions, and it's still discrete, so there's not so much change here. The next thing that we're looking at is the reward function, and the reward function also, the change is very small. We are, instead of having a fixed reward function, one reward for each state, we're now having we're looking at the whenever the score changes, we're looking at the new score, and we take the diff between the new score and the old score, and that's our lowercase r here, and that's our reward. Okay, so let's go back to the state space. We have to act here on this table. We have to get rid of it, and we're getting rid of it by replacing it with a what's called a deep Q network. And a deep Q network is a neural network with a couple of convolutional layers in the beginning, used to process this input image. They're stacked up. They are separated by ReLU nonlinear activation functions, which is still a very common thing to do even today. And to quickly explain how convolutional layers work in a network, they're always used when there is an image input, because they're good at recognizing local features of the image, and they can learn these features automatically. And the more you stack up, the more convolutional layers you use in the beginning, the higher you get in the hierarchy of in terms of the features that you capture. So, for example, I would think that the first convolutional layer is able to automatically learn things like these two eyes here that are next to each other. That's a pretty low-level feature, 2 black dots next to each other. Pac-Man has a couple of diagonal lines here, that I'm sure this first layer will capture and learn. The small dots it will definitely learn, the large dots it will learn. It will learn lines like this, the horizontal ones and the vertical ones. And then pass these observations onto the next convolutional layer, which will pick it up, these basic low-level features, and then learn how to combine them and to recognize more complex shapes. For example, this cylindrical shape of the ghosts, the round shape of Pac-Man, maybe entire blocks here, like these rectangles. This is some stuff that the second convolutional layer would learn, and this is all fully automated. And the third one, if you added a third one, you would probably learn to distinguish entire objects, like a ghost, and maybe even distinguish the ghosts because they have different colors, and so on and so forth. The last convolutional layer we are going to flatten out, so that we can connect then a couple of fully connected layers, also known as dense layers. And they are here to then make sense of all these image features that the convolutional layers have recognized. And in the end, we have this is what's called a softmax layer, and it outputs the predicted Q values for each action given a certain state. So it's a little different from what we know from this vanilla Q function here, where you put in a state and an action. This works a little different. You only put in a state, but you get as output a whole array consisting of one Q value for each action. And they did this, I believe, I remember, to save on the number of runs they would have to do through the network. Right? You could imagine if you have to try every action, and it works like this here, you would have to input every action alongside this state and only receive a single value here. It's much more efficient to just put in the state and get all action values at the same time. Of course, this will make the Q network have to adjust its weights differently. It will basically have to learn how to do this. It's a little different the way it learns them, but in practice it's the same thing. You reach the same goal, and you do it more efficiently. You can do things more efficiently this way. Now that we have a neural network instead of a Q table, a neural network that approximates our Q function, of course the last thing that changes is the update rule. But the update rule is still, the new one that I'm going to show in a second is still very similar to this original one. You will see in a second that it's still at the core of it, you still have the original estimation of the current state and the action that we took, and you take the difference between that and the new estimation of the same state action tuple, which is the sum of the reward that you observed plus the Q value of the next state, because you ended up in the next state. You have to just simply add it to the reward to get an estimate for this particular state action tuple. And I'm going to show this to you. This is the loss function. This is not the update function, but you can derive the update function from this loss function. This is the loss function for the neural network, and here you go. Here you have this same thing basically. You have the original belief or estimate of your state action pair, and you do the difference between that and the new belief of the same state action pair, which is the reward that you receive plus the value of the Q value of the next state. Okay, you have the square here because it's a loss function. You're doing a squared error, and you also what this means here is you're sampling differently from the environment. So instead of remember what we did when we did the Q learning, the traditional Q learning, we went through the episode frame by frame, action by action, and everything was updated. The Q table was updated in the same sequence that we ran through the environment. Now what they do here is they play the game, and while they play the game, they record SAR as prime tuples. So they basically they capture an experience here. Let's say the Pac-Man runs from here to here, and then they they cut it. They split this up into single frame SAR S prime observations and store them and store every single SARS tuple independently in a database. And they do this, I think they have a storage size of 1 million of these experience tuples. Once they reach the million, they start throwing out the old ones, and what they do here is they do stochastic gradient descent, like in a normal supervised learning setting, but they sample each batch uniformly, meaning IID, so independently and identically distributed. And this way, by doing this, in this strange way, they are able to stabilize this whole thing, because it's very hard. It's much harder to train a neural network on this kind of data with this kind of loss function than to train a neural network on supervised, manually curated data sets. And the reason for that is because your target term in the loss function, this is the target term, that's usually in a supervised learning setting, that would be your y, and this is your y hat. This is what the network thinks the value is, and this is what you as a supervisor would put in as the value. But the problem here in reinforcement learning is that this term here is also an estimation. It's not something that we can supervise, that is manually curated. So this brings great instability or instability to this training process. And this was one method, this uniformly sampling single SARS experience snippets from the database was one way of stabilizing it, stabilizing this training process. The other trick that they did, and these were the two breakthroughs here in these papers, and this was the main reason why this all of a sudden worked. The second trick they did was to use a separate target network. So basically, when you pull this value here and when you pull this value, you use two different networks. And this network here, this target network, is always, they are generally the same, but this one is always a few steps behind. It's always like some parameter of steps behind, like n steps behind. And this also, this only interval synchronization between the two leads to more stability. Yeah. Whereas in classical Q learning, remember, these were the same. This was the lookup on the table, and this was a lookup from the same table. Yeah, so they were the same. In this case, this one is always a little bit behind, which means it has more stability. Yeah. Okay, I went a lot into the details now, but it's okay. You can. I recommend you read the paper. This, especially the 2015 one. It was a Nature letter to Nature, I believe, and it was called "Playing Atari Games at Human Level with Human Level Performance." I believe that was the title. I will show the title later in the references. It's a really good paper. It's very simply written, and what I think is truly fascinating here in this whole thing is that a lot of the elements of the original Q learning algorithm are still there. So that I found really cool. Let's look at some results. This is actually the results that we see here for this method. We have a bunch of games here. I think it's 3, 6, 9. It's a few dozen Atari games. Pac-Man is here. It's actually one of the ones that perform really poorly with this network. But this line here separates the games that performed poorly, below human level, and all this bunch here is the games that performed at human level or better. Okay, so everything that has a score of higher than 75% is considered human level. Yeah. What they did here, funny story, they invited people to their lab in London and they set them in a room and they had to play video games, and then they measured their performance. And this was the human level performance that they measured this way. Sorry, they have this gold standard here, like a machine learning gold standard, which is the gray stuff, the gray bars, which is a linear approximator. That is a method that uses a linear model, so it doesn't use a neural network, but a linear function approximator. and the blue one is the actual result from this particular network here. Yeah, what's interesting here? I find it interesting that games like Pinball and Breakout, where you have these kind of bats and you have to hit the ball, are scoring really well. And I'm assuming that it's because they're a little easier, especially for the computer to play, because I could imagine that, for example, when you play Breakouts, all you have to do is kind of move the bat always on the same latitude as the ball, and then you should always be able to hit it. I understand that sometimes the ball makes crazy moves and it bounces from somewhere, but still, I think that's one of the reasons why these performed so well. The other one is boxing. Okay, that's also funny. Much better than the human performer. Anyway, so these are the results, and let's move to the last paper that I want to discuss today. We have here. This is the Intel group. This is published in 2017. I will do this really quick. They use a different model. It's not really a deep Q network anymore, and I will not go into details here what they do exactly here. What I can say here is what's interesting is that they use a 3D environment. So this is a big change to before. It's the input is still an image, as you can see here. They use this is a convolutional neural network with many layers, with many convolutional layers, 5 to be precise, and it's the same methodology as before, but the images are now coming basically from a camera on top of the playing actor, or on top of the playing agent, and the agent is in a maze, and it has to run around and collect these health kits here while avoiding these blue, I think they're bombs or something. And what's really amazes me is that it can recognize, or it seems to recognize pretty well what a wall is, even though the wall has some texture. Also that is amazing to me, and also the fact that it recognizes the 3D level structure. That's one thing, the 3D aspect, but the other thing is also that this is a partially observable Markov decision process, because the agent is not able, or the algorithm is not able to observe the entire environment at any given time. Yeah, it only sees in one direction. It has maybe a 90-degree field of view. So this is pretty amazing that they reach these results. I mean, it's only a short video, but it looks pretty cool. Here, for example, I noticed that it was in the corner. It turns around. Here it avoids the bombs, and so on and so forth. And this particular method, even though I said it here, it's not policy gradient. Policy gradient is another class of algorithms, which is now basically the gold standard. It has replaced deep Q learning as the gold standard, and it's a class of methods that doesn't approximate the Q function, but it approximates the policy function directly with, for example, a neural network. But again, this one is not policy gradient. It's even beyond that. It's a rather complex topology. I don't want to go into too much detail. You can read the paper. It's a very interesting one. It's also not tough on the math, so it's I found it easy to understand and very intuitive. So yes, thanks for listening. These are all the references that I used today, more or less. What's really great is this book here. If you want to go into reinforcement learning, I highly recommend reading this book. It's a very good one. It explains everything absolutely from scratch. You don't need to know much in advance in order to become almost an expert in reinforcement learning. Once you're finished with this, it even covers these newer methods that we just discussed. It has references to the deep Q network. It talks about neural networks, policy gradients, all the theory behind policy gradient. So it's really cool, and it starts absolutely from scratch. So you will learn methods that are come even way before Q learning. It will cover the MDPs and everything I talked about today. Anyway, plus many more things. And these are the papers here. These from 2 to 5 that I used. And this is my information here. So you can email me, ask me questions. You can there's a repository on GitHub where I have a single Python file here that runs this Q-learning algorithm, this simple Q-learning algorithm that we covered today. And yeah, also this is the link to our meetup group. It's the Düsseldorf Machine Learning Meetup Group, and we have a Google Drive. There's a folder talks, and if you're a member of this group, you can access this PowerPoint presentation. Yeah, and so thanks for watching. Thanks for listening, and until then, bye bye.